Hello everyone, welcome to G-Centric. So in this lecture we will move on to the RC circuit. So in the previous lecture we have seen about the RL circuit. Now we will see on the RC circuit. So now the V of t is given, that is Vm cos omega t, and current I is flowing in the circuit. So when current I enters, this is positive, negative, and this is positive, negative. Since it is a series circuit, there will be voltage drop across R and C. So that voltage drop, let it be VR and Vc, okay, and this total voltage be V. Remember, it is a vector product, okay, so not a product, vector sum, okay. So basically this V is vector. So there is a difference between vector addition and a normal addition. So when we will solve the problems, we will look at that, okay. So now this is nothing but total V is equal to VR plus Vc. Okay. Now it is VR plus Vc, same thing we will apply. So V is equal to, this is again vector, I R plus, since it is series, current is same, so it is I, and this will be what, minus jXc. Okay, so this C is minus jXc because we have seen it is the separate element. When we have taken it, we have seen why it has come negative. Okay, so this is jXc minus jXc. Okay, so what I can take? I can take I common and write R minus j into xc. So this is nothing but Z. Okay, so this is I into Z. Okay, so where Z is equal to R minus jXc. Okay, so now what I will do, if I have to take the magnitude of this one, so if I have to take the magnitude, what I will write, R square plus, it again if it's plus or minus, what will happen, it will be same value. Okay, so it will be xc square. Okay, so now after this, for the magnitude of this one, what I have to take, for the phi, angle phi, it will be tan inverse of xc by r. Okay, so this is the phi angle. Now whether it will be minus or plus, here okay, if it was square, so it became minus into minus plus, but here it will be minus xc upon r. So if I have to, I will take the minus over this side, that is minus phi will be tan inverse of xc upon r. So when I take that one in this side, then what will be Z equal to mod Z minus phi. Okay, so I can write it as mod Z minus phi. Now for the current, if I have to calculate the current, it is V upon Z. So V angle is Vm by root 2. What is the angle? Since it is cos, it will be 0 degrees. Next Z is, we have taken here mod Z minus 5. Now Vm by Z is equal to, so I is equal to Im by root 2. Okay, so 0 minus 5, if it goes up, what will it become? 90 degree. So if it is positive 90 degree, positive phi, I am sorry. So this is positive phi. So it means that I is leading. Okay, I leads V by 5 degrees. So this is the meaning of the this r square plus x square, and when you take the minus sign outside, then it will come here as negative, and when it comes negative, and if you take the value of I, that comes out to be V by Z, and substitute the value RMS values. Okay, so Vm by root 2 is nothing but VRMS. So when you take up, it will become minus 5 will become plus 5, and that means that if it is plus 5, then it is moving in the anti-clockwise direction, hence I leads V by 5 degrees. Okay, so now we will see what is the instantaneous power. So power is nothing but VRMS into IRMS cos phi, or you can write I square RMS into R, and what will be the reactive power? IRMS VRMS into sin phi. Okay, so now we will see the representation of the phasor. Okay, how we will represent for this phasor? Okay, so first of all what we will take, this is nothing but reactive power, VAR. Okay, so this active power and reactive power we will see when we will study the power triangle. Okay, in the concept of power we will see this one. Okay, so after that we will see the vector representation. Now V, what is the value of V? Okay, let me write here. Here it is. So V is equal to Vm by root 2 0 degrees. So I is Im by root 2 plus 5 degree. Then what it is, we have got, okay. So if I take V as a reference, here is V. Then if I move further, okay, or here somewhere, whatever may be the magnitude, depending on the magnitude length, we will mark the arrows. Okay, so here it is V. This is VR. Okay, we have taken this voltage as reference, VR. Then what we will do, the current is after flowing from this resistor path, it moves to the capacitor. So for the capacitor, what is current doing? It is leading by 90 degrees. Okay, so this is 90 degrees VC. But for the triangle of vector addition, what it should be, we have to shift here, because the tail of one vector should touch the head of the another vector for the triangle of addition. So this is VC. Now I will rub this one without shifting the angle, that is 90 degrees. If here also it was 90, here also it will be 90 degrees. So when I join this one, I will get the total vector V. So how can I write this one? So magnitude of V vector is nothing but square root of VR square plus VC square. So what is the angle? Tan inverse of VC by VR. So this tan inverse indicates VC by VR. So VC can write as Im by root 2, and here VR we can write it as, sorry, this is Jx minus Jxc. Okay. Then here we can write it as Im to R. So this gets cancelled. So we are left with tan inverse of Xc upon R. Okay. So here it is minus 5. This is tan inverse Xc by Xr. Okay. So this is the how you can take out the value of the angle phi. This is phi. So if you have to draw the impedance triangle also, it will be same. Okay, here it is R, then here you have got Jxc, then here you have got Z, and this is phi. Okay, so this is how you can write the impedance triangle. So now this is about the RC circuit in series. We have seen RL, RC, then we will see now the combination of R, L and C. So how we can, and there are number of cases, 3 cases are there. When L and C will come, XL will be greater than XC and XC when greater than XL, and when C is equal to L. Okay, so there are 3 cases, we will see how it will vary. Okay, we will see the RLC network, okay, which are in series. So R, L and C are connected in series. So when they are connected in series, then there will be having voltage drop across each of the element, that is VR, VL and VC. Okay. So now similarly again we will write it as total V. So this V is equal to VR plus VL plus, okay, so VL plus VC. Okay. So VR plus VL plus VC. Now I is flowing here, so it will be I into VR, I into R. Then we have got I into JXL. Then we have I into minus JXC. So now this I is common. I is common. So what will be inside? R plus JXL minus JXC. So this we will replace it as Z. Okay. So where Z is equal to, Z is nothing but equal to R plus JXL minus JXC. Okay. So now if I have to take the mod of Z, then it is root of R square plus J into XL minus XC whole square. So whatever the value will be, it will be same. If it is minus, it will be the square root, so again it will become plus. But whereas for phi, it will become tan inverse of XL minus XC upon R. Okay. So this is the RLC circuit network for finding the impedance. Now if I have to find the value of current, V upon Z, V is nothing but Vm by root 2. Here phi is how much is the volt degree? It is 0 degree. So this Z is 5 degree. Okay. So 0 is plus 5 because I will be equal to Vm by root Z is nothing but again Im by root 2, it is 5. Okay. Okay, so this phi basically I have taken in general terms. It can be either plus phi or minus phi depending on the value of the capacitive reactance as well as inductive reactance. So if XL is greater than XC, then it will be inductive and current will be lagging, so we will get here minus. But if it is XC, then we will get plus because current is leading in this case because of the capacitive reactance. So we one by one we will take case 1, case 2 and case 3 and we will see what are the things we will get. Case 1, what are the things that we will get for the impedance, 5 angle and the current. Okay. So first case is, let us take XL is greater than XC. So when we take XL is greater than XC, this becomes inductive circuit. Okay, the dominant will be inductor. So the dominance will be of inductor. Okay. So this is inductive circuit. So now what are all the changes that we will get? So here it will be same, XL is greater than XC means okay, Z will be R plus J into XL minus XC. Okay. Yeah. So here Z is equal to R plus J XL minus XC. So what is the magnitude of this one? It will be R square plus XL minus XC whole square. Okay, so its angle will be tan inverse of XL minus XC upon R. Okay, so now what will be the value of phi? It is Vm by root 2. Since it is cos, the angle will be 0 degree. For this Z, it is nothing but mod of Z plus phi. Okay. So here also we can write it as mod of Z plus phi degree. So after writing it as phi degree, Vm by Z is nothing but Im by root 2 and this phi it goes up minus phi. Okay. So this is the value of phi. So I will write it here separately. V is nothing but Vm by root 2 0 degree and I is Im by root 2 minus phi degree. Okay. So let me rub this one. After writing this, we will draw the phasor diagram of this one. Before that, what is the instantaneous power? It is same as Vrms into Irms cos phi, and if you have to take the what is reactive power, it is sin phi, that is Vrms into Irms into sin phi, that is the reactive power. Or for the active power, again you can write it as I square Rms into R. So coming to the phasor diagram of this one. So first what is the reference that we will take? V. So here is VR. So what is the magnitude of this one? Current I, they are always in phase. So when it is resistive network, they are in phase. So this will be I. Okay. Then it is going to the XL. So if it is XL, then what will be the current is leading or lagging? It is lagging. But with respect to VR, what we will get? We will get here positive sign. Okay. It will go in this direction with respect to voltage, because we are taking voltage as the reference. Okay, so voltage will be plus 90 degree, but for the vector addition, what we will do, we will shift this over this side with the same angle. So with the same angle, we will shift it here. So this is VL. Okay, now VC, it will go to VC. What will happen to the current? It will be leading Okay, so but with respect to voltage it will come here, but for the sake of vector addition we will take it here, that is Vc. Now this Vc is smaller than VL because we have XL greater than XC. So if I take this one upwards, okay, if I take this upwards, then it will become negative times of Vc, and this vector is nothing but VL minus Vc. Okay, so here somewhere we will get VL minus Vc, and by the triangle law of addition, if I add this one with the angle phi, then I will get the total value of the vector V. So what is its magnitude will be root of VR square plus VL minus Vc square. Okay, so next after this angle phi will be tan inverse of VL minus Vc divided by VR. So when you take I common, okay, when you take it as I into X, XL and minus I into XL upon IR, II gets cancelled. So again the angle will be tan inverse of XL minus XC upon R. Okay, imaginary upon real. So this includes J terms, so it will be imaginary upon the real part. Okay, so this is about the RLC circuit. First case, case number 1, what was it? XL greater than XC. Okay, same thing we will take now for the case 2. Okay, coming to this second case, that is XC greater than XL. Again, if you take the, okay, let me write in, okay, so this is capacitive, it is a capacitive circuit because the dominance is more of the capacitive network. So now what we will do, we have got Z is equal to R plus, okay, so XL minus XC, where XC is greater. Okay, so this will become XC minus XL. So magnitude of this one will be equal to, it will not be any difference because it is in the square. Okay, again it will comes out to be positive. So this is over, then what will be the phi? Tan inverse of imaginary part upon real part. Okay, so magnitude of Z is equal to magnitude of Z upon phi. Okay, so this will be minus phi. Okay, this is because minus Jx. Okay, so it will be minus. Next, what will be there? Z is over, then if you have to calculate the value of current, so what will you get the value of current as? V by Z. So V is nothing but Vm by root 2, 0 degree because of cos. Then for this one, magnitude of Z minus 5 degrees. Correct? That is because why this minus is there? Because XC is greater, which has got the minus JXC. So now this Vm by Z I can write it as Im by root 2, and this minus 5 will go up, so it will become plus 5, which means that I leads V by 5 degrees. Okay. So now again the what will be the power? Power for this one is again same thing, Vrms, Irms cos phi or I square Rms into R, or the reactive power will be sin phi. Okay, here it will change. Okay, that is because we will see in the active, because in the power triangle we will get here as sin phi. Why we will see in the power triangle when we study the power. Okay, so now we will see the phasor representation of this one. So what will be here? We will take first VR. Why are we taking VR? Okay, when current I flows here, we know that V and I are in phase for the resistive network. So when it is VR, so here it will be somewhere I. So next it is flowing to the XL. Okay, so we will draw here. Basically it will come here with 90 degree. Okay, leading. That is because we are drawing it with respect to VR. But in inductor what will happen? Always current lags voltage by 90 degrees. So we will draw it here, we will shift it because of the vector addition, and here it will be 90 degrees. So next, when it comes to capacitor, what will happen? Current always leads. Okay, but because what with respect to voltage, what will happen? It will come downwards. So this is Vc. Now what we have taken, Xc is greater than XL. So we will take this VL downwards, which will become negative. Okay, so this is VL, and somewhere here we will get Vc minus VL. So and its sum will be, this is total V. Okay, so now in the power triangle, sorry, it's not a power triangle, voltage triangle. Okay, because all are with respect to V. Total magnitude of this V will be equal to VR square plus Vc minus VL whole square. Then the phi angle will be tan inverse of Vc minus VL upon VR. So now since it's a series network, I and I will be common. So it will be Xc minus XL upon R. Okay. What happens? Current will be positive. Okay, here you have got the positive current leads in the capacitive network. Okay, that we have seen in the previous lecture when we studied separately only about the capacitive network. So this is all about the Xc greater than XL. Now there is one more third case, that is called as Xc is equal to XL. So when we have got Xc is equal to XL, okay, case number 3, when Xc is equal to XL. So what was the Z we had got in the derivation? R plus JXL minus Xc. Okay, we had got this one. Now whenever Xc is equal to XL, so this whole term will be equal to 0. So that Z will be equal to R. So if you have to calculate the I, what we will get? Directly V by R, or you can take it as Im by root 2 with an angle 0 degree. So now I is equal to 0 degree, Vm by root 2 is 0 degree. So how will you draw the phasor? This is for VR and here is somewhere I. So they are in phase. Okay. So if you have to calculate the angle, what you will get? What was the angle that we will calculate here? Here it is term is 0 and 0 by anything is 0. So phi is 0 degree. Okay, so what you will get the power? Vrms, Irms, cos phi. So when you put cos phi, phi is 0 degree, cos 0 is 1. So what you will get? P is equal to Vrms into Irms. Okay, so when you draw the phasor here again, if you take this is VL and this is Vc. Okay, basically if they were in not phase, but now XL is equal to Xc. So this both will cancels out because they are equivalent opposite to each other. So that is why wherever you get XL minus Xc, that term will be equal to 0. So here also this is 0 and R square is R. So magnitude of Z is equal to R. Okay, so this completes the RLC network in this series. Okay, so in the next lecture we will see about the parallel circuits. Okay, RL, RC and RLC parallel network. Okay, thank you.